Okay, so we are talking Beer's law. It's week 2. We did Beer's law last week. We did the absorption lab, and the question is what's going on with Beer's law. Now, fundamentally, Beer's law is kind of experimentally determined. We can actually do our lab differently, where instead of me telling you what Beer's law is, you have to experimentally determine what Beer's law is. And so what this guy realized is that there's some coefficient, there's some relationship between absorption and concentration. And so kind of like density, kind of like molecular weight, like density is, let's write density real quick. Density is mass over volume, right? Yeah. And so one of the big mistakes that students make is they think, oh, if you cut concentration in half, then epsilon would cut in half. But that's not actually true, because epsilon is the ratio of absorption to concentration. It's supposed to be a constant. So what happens if concentration goes down, absorption also goes down to keep the ratio the same. And we see that exact same thinking happen with density. Come on and grab a chair. So with density, if our volume goes down, our density doesn't decrease, our mass changes with it to keep this ratio the same. And so that's that relationship. Density is this property of material. Epsilon is this property of material. The catch is there's a little bit more than just the concentration. There's also the path length. And so for us, most of the time, we do this situation where we say, hey, path length is 1 centimeter, right? It's always the same thing. It's just equal to 1, and so we can kind of ignore it. And then this molar absorptivity, this behavior of the material, is just the ratio of absorption to concentration. So path length, the way we can make sense of this is if you've ever looked into a shallow pool versus a deep pool, you know, it's harder to see to the bottom. That's because your path length is changing. For us, since we're always doing same path length, it's not as much of a concern. But if you pour liquid into like a thin container versus a really thick container, it's harder for the light to get through the thick container because essentially there's more particles that the light is running into, more chemical compounds. So this becomes kind of how Beer's thought about it. And then just a little bit of a rearrangement makes it A equals epsilon BC, where again, B is path length, not wavelength. So you'll notice in this equation, there's no wavelength in this equation. So there's no place that wavelength shows up, but we use it as essentially a reference system, because epsilon will change with wavelength. So while this property doesn't change with concentration and absorption, different materials absorb light in different ways. And now we've kind of seen that, right? So when we saw our absorption spectrum for our blue dye, we saw nothing, 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 and we saw it absorb over here, right? And so we can see that as the wavelength changes, as that wavelength changes, there's places where it doesn't absorb and there's places where it will absorb. And so we just say, look, we're going to take this wavelength as our lambda maximum, and we're going to use that as our reference system. Now, what that means is, as long as the lambda max isn't changing, we don't need to worry about it. The only place we have to be worried about lambda max is if the problem has like 2 different lambda max values, something weird is going on, right? Because if I measure here and I measure over here, I'm clearly going to get 2 different absorbances. So like that value matters, but as long as that value is constant, we don't need it. It's just the fact that it's not changing is what we need. So we've got this equation, we've got the different parts of it understood, we've got this a little bit more depth in terms of why we don't see wavelength, but we do see path length. So let's look at some specific problems. Now you said you had a specific problem from the lecture slides?
Yeah, so this one's, what is the molar absorptivity of an 11 micromolarity solution with an absorption of 0.836?
So what is molar absorptivity of a, what was that concentration?
11 micromolarity solution.
11 micromolarity solution.
With an absorption of 0.836.
0.83?
Yeah, 0.836.
Was there anything other information?
No, that's it.
Okay, cool. So we can kind of do this in the same way that I've talked about it before, right? We can look at what's explicit, what result are we trying to get to, and then what's the implied information that's missing in the middle. Right, so I'm just going to make an explicit list, and I like this process particularly if I don't know how to start a problem. I always go to this and be like, well, what did they tell me? Right? So I've got an absorption equals 0.836. I've got a concentration of 11 micromolarity, and I'm trying to get to an epsilon. Right? And then after I have the parts I know, I look at my equation sheet and I say, okay, what on the equation sheet has these three things? Right? And it turns out it's already on the board. It's that one. Okay, so I look at this and I say, okay, which parts do I know? I know A. I know C. I'm trying to find epsilon. What parts are implied that they don't tell us, that they just assume we know? Thing number one that they assume we know is Beer's law. Right? Just the fact that we're using that equation is part of something they assume. Right? And the fact that we say concentration, molar absorptivity, and absorption, those are all hints. None of it says Beer's law. But those are all things that lead us to think, oh, it must be Beer's law. Right? Or that's what is implied. Second thing. What else does it not tell us that it assumes we know?
1 centimeter wavelength, or not wavelength, path length.
Yeah. It assumes, right, that we know the path length is standardized. Right? And this is one of those things I mentioned in class. If we don't give a specific path length different than 1 centimeter, it's pretty safe to assume that it's a 1 centimeter path length. There are very few questions where I say, hey, what happens if the path length changes? But there's a couple of those in there too.
Okay.
But most of the time, there's that. Last thing that it assumes we know. That 11 micromolarity is 11 times 10 to the minus 6 molarity. There's no place where they told us to do a conversion. There's no place where they said, hey, don't forget to convert your units. But that's something that we should know, right?
Yeah.
The molar absorptivity is usually given in units of concentration, so I need to do that conversion. At that point, right, I figured out that thing. Now I just rearrange the equation and solve for epsilon. Right, so I'm going to end up with epsilon equals A over BC. Plug all of my values in. All of my calculators are in a pile over here right now. So I do 0.836 divided by 1 centimeter divided by 11 times 10 to the minus 6. And I end up with a value of 76,000. My units on this would be 1 over molarity centimeters. The units don't make total sense. The units are just there to make sure that we end up with absorption having no units.
Mm-hmm.
Now, does that value for epsilon make sense? Do you remember the possible range? I put it on the board.
Wasn't it like 10,000 or 100,000 or something like that?
That's the range. 10,000 to 100,000 is the typical range we see for a lot of the materials we're dealing with.
Yeah.
There are things that have much higher epsilons that absorb light a lot better, and there are things that are lower than that. There are things that almost absorb no light, that have really low epsilon. But most of the things that we look at that act as pigments and act as colors have that range of 10,000 to 100,000, and this falls in that range.
Okay.
Wait, I'm confused how you got the units to be 1/m times centimeters.
So notice my concentration, if we look at the units of everything that's here, absorption, no units, right? Because it's a ratio of intensity to intensity. This doesn't have any units. Path length is in units of centimeters. Concentration is in units of molarity.
Okay.
Now, you'll see this written different ways in different places. Sometimes you'll see it written down. Let me make sure this is all on the screen too. Sometimes you'll see this written down as liters, moles, centimeters. And all they've done is taken that capital M molarity and turned it into moles over liters and rearranged it. And so you can see it either way, and both are correct. I like the molarity centimeters because it kind of tracks with the equation easier for me. But I also like the liters, moles, centimeters because when I'm doing calculations, it makes it easier to cancel out the correct units.
Okay.
So they're both useful at different times. But they're equivalent to each other. You could do either one and you would get credit because they mean the same thing. So that was one of the Beer's Law's problems. Do we have another one you want to look at, or do you have one you want to try on your own?
I have another one I want to ask, but I know they came over for all
Yeah.
So.
Do you guys also have Beer's Law questions, or do we want to move on to something else?
I have loads of questions. I have questions about everything.
Can we go over the dilution
Yeah.
question?
So that is relatable to Beer's Law, right? We've got concentration. We can think about this in a pretty simple way. If you add water to something, does concentration go up or go down?
Goes down, doesn't it?
Does it stay the same? No, it doesn't, right?
Up, down, or stay the same? Think about like you make Gatorade. You dump water into your Gatorade. More concentrated, less concentrated.
Less.
Right? You dump water and it gets less concentrated.
Mhm.
You dump more Gatorade powder in,
It goes up.
more concentrated,
Yeah.
right? So what's happening there, and the reason I use the Gatorade example, or just like any powdered drink example, is like these ideas, for some reason when we see them in a chemistry class, we're like, hold on, it's got to be a trick. But it's not, right? Really at its root, chemistry is just trying to describe the world, and then in the process finds out the world's more complicated than we thought. And so then it gets kind of weird, but we can always start with like a really simple, like, okay, so what's something I understand with like dilution already? So what's happening with dilution is essentially we're changing our concentration. So let's look at the concentration equation. Is it okay if I erase this?
Yeah, it's fine,
Yeah. Okay. So let's look at the equation we have for understanding concentration and see how dilution affects it. So our equation that we have for just concentration, for the concentration we're using, we're doing molarity, and that's molarity equals moles of solute over total volume. Of the entire solution, right? So we can imagine. Let's do this. Let's do this in a simpler way to start. And just kind of think about it. Okay. So I've got a container. It's got some water in it, and I make a lime Gatorade. Now it's got some amount of lime Gatorade in it. The amount would be a number, right? That's where it's going to be moles. Right? So I could say this solution has a concentration and a volume associated with it. We'll call it concentration 1 and volume 1. Dilution specifically is just adding water, right? Not adding more Gatorade. So if I just add water, my volume goes up, and my Gatorade, having 2, 4, 6, 8. My Gatorade is the same number of Gatorade particles, but now it's in a bigger volume. Now I'm going to add one more thing here, and this is going to be right. So I've got my N, so I've got my concentration, my volume, and my number of moles, my moles of Gatorade. Now, which of these three things, and these three things relate to each other, right? Moles, so I can relate these three things to each other. I can do concentration 1 is equal to moles 1 over volume 1. Or I could rearrange it where I've got my moles 1 is equal to my concentration 1 times my volume 1. Right? Just rearranging that equation from this definition of concentration for molarity. Now, out of these three things, here's the important question. Out of these three things, which ones do change and which ones don't change? Let's do the obvious one first. Does volume change?
No. Or yes.
Yes. Right? We added water, volume definitely changes. So we're going to have a new volume here. Volume is definitely going to be different. Does concentration change?
Yes.
Yeah.
Yeah, concentration changes. Does number of moles change? No, right? My moles so I can erase this subscript of the 1 and this subscript of the 2. My number of moles stays the same because I only added water. Now what this means is I have a second equation over here where M equals M2V2. Now I can just set them equal to each other because the number of moles is the same. So I have my original molarity and my original volume. That gives me my number of moles. That's going to be equal to my new molarity and my new volume. Whoa, I wrote M twice. That's not what I was supposed to do. My new molarity and my new volume. Hey, come on in, grab a chair. Right, so the fact that my moles didn't change because I only added water means I can set my concentration and volume before I added water equal to my concentration and volume after I added water. So that's all the conceptual work. Like that's all the thinking behind it, right? Mm-hmm. So this means how do I turn this back into understanding my Gatorade isn't as tasty because I added a bunch of water to it, right? So we can essentially say, look, I can make sense of like how my volume change affects the concentration by now working with this equation down here. This is the dilution equation. And now we can look at the same kind of problems we've been looking at, and we can understand dilution just by saying, okay, well, which of these variables do I have, which ones don't I have? So do you have a problem you want to look at?
Yeah.
Okay. Let's look at a problem now.
Wait, why is concentration using M and moles using N?
This is by convention, so N is usually what we use for number of moles. V is for volume. M is specifically concentration in units of molarity. So concentration is generic. It could be, there's lots of different ways we talk about concentration. But when we are doing moles of solute over total volume of solution, that's specifically molarity. And that's the one we're going to be using this quarter. If you take Chem128, you talk about molality, you talk about percent by weight, you talk about some different concentration values that are useful in different situations. But for us this quarter, just molarity. And often molarity is the easier one to use. Okay. I'm going to erase a bunch of this. I'm going to move this equation up here. So this is the conceptual thinking of what's going on. And now we've got our dilution equation.
I've got questions as well, like for dilution. If you
M1 V1 equals M2 V2. That is our way of thinking about dilution. Right, and essentially we can rearrange this if I bring the volume over. It's like if I change my volume, my concentration goes down. Right, which is the same thing we thought about with our Gatorade. Or if I have Gatorade, I dump water on top of it, my Gatorade's less concentrated now. So this, even though this doesn't we've probably never thought about dumping water on top of Gatorade in terms of M1V1 equals M2V2, that's what we've been doing. And so now we've got this extra dimension. Now every time you're mixing stuff together, whenever you're cooking or making drinks, you're going to be like, I'm doing a dilution, aren't I? You are. Did I just do an M1V1 in my kitchen? You did. So let's look at a specific problem.
So the problem I was looking at is a second part of a question I already answered.
Okay, let's get the first part and the second part.
Okay.
And where is this question coming from?
It's on the absorption preparation.
Okay. So we've got abs prep. This is the abs 2 prep that we're doing. Okay, cool. So what's the question?
So the one I'm having trouble is if you use 32.0 milligrams of the stock solution from the previous question and add water to make a new solution with a total volume of 50.0 milliliters, what is the concentration of dye in the new solution?
What was the total volume?
So the total volume, sorry, of the new solution or the
Of the
previous?
new solution.
50.0 milliliters.
Exactly 50 milliliters. Okay. So what was the concentration of the stock solution in the previous problem?
It was, let me see. It was 1.284 times 10 to the negative 4 moles.
Was that moles or molarity?
Molarity, sorry.
Molarity, okay, capital M.
Yeah.
Cool, okay. Important difference. Okay, so that's 1.284 times 10 to the minus 4 molarity. That's 128 micromolarity. That's fine. Okay, so how do we solve the problem? Where do we even begin? Let's do the same thing that I like to do, and we're just going to set up this thinking. Oh, that's not where I meant to write that. So we're going to look at our explicit information. We're going to look at what result is trying to get us to, and then we're going to see if we can figure out what is being implied, what the question is not saying that it's trying to make us think of. So I'm going to go ahead. I notice I've got a first volume of 32.0 milliliters. I've got a second volume of 50.0 milliliters. I've got a concentration from the previous problem. Should I call it, I'm just going to call it an M for now, not an M1 or an M2. We'll figure that out. Of 1.284 times 10 to the minus 4 molarity. And, oh, I didn't write down, there's the, I'm missing part of the question.
Which part?
What is it actually asking for?
Oh, sorry. So it's going to be the, it's a lowercase m and an uppercase m, so is that micro?
But like the end of the question, it says, and you total volume 50 milliliters. Does it say what's the new concentration, I'm hoping?
Yeah, what is the concentration of the dye in the new solution?
I started looking at the problem and I was like, wait, it's not asking anything. Okay, what's the new concentration? So then I say, okay, I've got some new molarity. Now I'm going to go ahead and put a label in there. It's got some new molarity that it's asking me to figure out. This is the first molarity. Okay, so then I look at the four things. I've got four things. I've got three things I know, one thing I don't know. And then we say, okay, well, what's being implied here? Dilution, right? We've got some amount of solution. It's at 32 milliliters. We dump water on top of it till it gets to 50 milliliters. It's doing a dilution. So we're going to have this thing, M1V1 equals my number of moles. And then my number of moles also equals M2V2. Right? Because I'm only adding water. My number of moles is not going to change. That's going to be the same. So I can just say M1V1 equals M2V2. And now I can plug things in. I've got V1, I've got V2, I've got M1. So I've got, in terms of things I know, I've got 1, 2, 3 of these things in the equation. Now I can just rearrange and solve for M2. Does that make sense?
Yeah.
Right, so for me, this thought process of like just, because like I get lost in the words sometimes.
Mm-hmm.
And so I'm just kind of like, okay, well, what's the actual important information here? The words are important for the context and kind of the deeper thinking that helps get us this implied information. But once we've got that, we can just break it down into like the numbers, and I can start plugging things in. So I'm going to first rearrange this. So I've got M1, V1, V2 equals M2, and I'm going to plug in my numbers. I'm going to have 1.284 times 10 to the minus 4 times 32 divided by 50. Now notice, there's a nice trick here. I saved some math. Technically, you would have been completely correct to convert that milliliters to liters both times. But notice, my divide by 1,000 on top and my divide by 1,000 on bottom, that's going to cancel out anyway. Right? So my units here, I didn't give myself enough space for units. Let's give some units here. This is molarity. This is 32 milliliters. This is 50 milliliters. Notice my milliliters cancels out. So if I divide the top by 1,000 and I divide the bottom by 1,000, I'm just doing 2 extra steps that cancel each other out anyway. So I can plug this all in, and my M2 is already going to be in units of molarity. Now, funny thing is, if we left this as 128 micromolarity, our answer would just be in micromolarity, right? The same units would persist. So now, we can plug things in. And so this is kind of one of the funny things that we haven't gotten into with units too much yet. And I really don't get deep into it until third quarter chemistry. But like, the units you pick don't really matter as long as you're consistent. Like, you can do everything in milliliters as long as you keep everything in milliliters. You can do everything in micromolarity if you keep everything in micromolarity. Like, as long as you've got that consistency, it works out. But, and this is why, because we often have things that just like cancel out. Plugging in our numbers, 128.4 times 32, divide by 50, and we're gonna get, oh shit, let's do this, 1.284 times 7 minus 4 times 32, divided by 50, 8.2 times 10 minus 5. 8.2, let's do more digits there. 8.21 times 10 to the minus 5 molarity. So, no surprise, our concentration goes down. Right? Because we added water on top of it. The amount it goes down, the reason it goes down is because my original volume was smaller than my diluted volume, so this ratio is always going to be less than 1. This is dumping water on top of your Gatorade. You're not adding more Gatorade, so that volume's constant. Dumping water is going to make your total volume. Let me ask you a follow-up question. How much water did you need to add to make this happen?
52, I mean,
18.
Yeah, we're 50 minus 32.
Yeah.
Right? So we could figure out how much water you added to make this happen, but the thing we actually need is the total volume of the solution before the dilution and the new total volume of the solution after the dilution. And what was nice about this one, because sometimes we get problems where it's like, oh, you have 32 milliliters, you add 10 milliliters of water, what's the new concentration? They don't give you the total, you have to figure it out on your own by just adding the numbers together. The place where that creates headaches for students is they'll do V1 equals 32 and V2 equals 10. They'll forget that V2 is the total adding them together. So that's dilution. And you notice, hopefully you notice, I try to make it so when we're doing our math, it's always the same process. Figure out what you got, what equation are we supposed to use, plug in all the values and solve for the thing that's missing. That's going to be true like the entire quarter. Right? That's going to be applicable this entire quarter, probably in your physics classes, maybe in some of your math classes, some of your bio classes. It's always this like, okay, what did they tell me? What are they trying to get me to? What are they trying to make me think of? And it's always going to be that kind of like, you know, anytime you read a question in any class, you can always stop and be like, what are they trying to get me to think of? Because
And the 8.21 times 10 to the negative 5, that's in moles, right?
that's in molarity, because
Oh,
we were
sorry,
in
yeah,
molarity.
molarity.
Yeah.
Okay.
Right, so it stayed, since we were in units of molarity, it stays in units of molarity. Oh yeah, you can check if we're right. Did we get it right? No, I'm nervous.
So it's asking in that's micromoles, right?
Oh, it's asking for it in millimoles.
Millimoles.
Okay. Oh, because this was in millimoles and you converted it.
Yeah.
Okay. So if it's in millimoles, divide by 1,000.
Okay.
Multiply by 1,000. Multiply by 1,000. So you're gonna get 0.082. Right. So we have our answer in capital M for molarity. Is asking for an answer in millimoles. So that's going to be like 0.082 if I'm doing the math in my head right. I would say probably for me, one of the things that's most frustrating in LabPal is paying attention to units.
Yeah.
Because like you're doing everything right, like your answer is right, but it's checking for particular units. And if you don't realize, like, it's really easy to forget that there's letters underneath the box that mean something. And I think on one of the assignments, I forgot to put units on a couple of the boxes. And I have the units in the problem, but I like to have it under the box as well. And I think I forgot to do that in a couple problems. Okay, so that's dilution. Do we have another question we want to ask about dilution or Beer's law? All these things kind of relate closely to each other. Because here's the fun thing we can think about. If you dilute something, does the absorption go up or down?
Wouldn't it go down?
Yeah, how do you know?
Because the concentration isn't.
Concentration
Yes.
goes. Practically speaking, when you dump extra water on top of your Gatorade, does it get lighter or darker?
It's lighter.
Because it's absorbing less light,
Yeah.
right? We can go back to our simple kind of experience of the world and it makes sense.
Mm-hmm.
This is just trying to put all of this math and like detail to it so we can apply it to other situations that we have less experience with. But yeah, we expect if we dump water on top of something, concentration goes down, absorption should track with it, absorption should also go down. And that's actually the lab we're doing tomorrow, is we're looking at making a series of dilutions. So we're going to make a bunch of things at different concentrations, and we're going to see how that affects the absorption. So that way we can make a relationship. We're essentially going to figure out epsilon very accurately for one of the food dyes we looked at.
From the last lab? Or?
Yeah.
Okay.
And it's going to be like, so that's why it's called absorption part 1, absorption part 2, is because they relate to each other to some degree. Because essentially what we did last time was we figured out epsilon for like the blue dye and the red dye and the yellow dye with one data point, right? One measurement. That's not going to be great. So we're going to take like many measurements, but that means we need more information to make it work. But back to this Beer's law questions, dilution questions,
Question,
or other questions.
it's from 1.2, the
Sure.
homework.
Okay, I'm going to erase this problem for now.
it's number 8, and it says, an unknown sample of red dye has a measured absorbance of 0.442 at the A max of 516 nanometers.
Whoa, wait, hold on, slow down.
Sorry. Sorry.
Red
Yeah, I
dye.
could just show it to you.
Oh, cool.
It's right here.
Red dye has absorbance equals to 0.442
Two.
with
Yeah.
a lambda max equal to 516 nanometers. If the molar absorptivity at 516, epsilon at 516 is that 8,009 or 8,000? 8,982. And this has the split up units of liters, moles, centimeters. What's the concentration? Okay, so you notice when I'm breaking down the problem, I kind of already start doing my process. I write down the explicit information. I write down the result it's asking me to find, and now we just need to think about what's implied. Now, one of the things that becomes really important to get us good at chemistry, well, kind of at anything, right? When people ask me the number one thing to study, it's vocabulary. But it's not just getting good at the vocabulary words and knowing the vocabulary words. It's also recognizing, there's also chairs back there if you want to grab. And everyone scoot in a bit. It's also being able to associate the vocabulary with certain problems. For example, anytime we see the word concentration, there's like 5 or 6 different types of problems that can have concentration in them. Could be a dilution problem, could be a molarity problem, could be a number of moles problem, could be a Beer's law problem, right? There's a bunch of different things where the word concentration comes up. If it asks about absorption, there's a few different places where absorption comes up, but it's usually this. If it ever talks about molar absorptivity or absorptivity, it's only Beer's law.
Okay.
Right, so as soon as we see this epsilon idea, as soon as it mentions molar absorptivity, it's already implying A equals epsilon BC. Right, and so that's the kind of extra layer of vocabulary that we need to be practicing. Not just I can recite all of the definitions because I memorized them all, but I have this understanding of how the different words relate to different ideas, and they help clue my brain into what I'm supposed to think about when those words come up.
Okay.
So, concentration, good word to know, cuts us down to like 4 or 5 possible problems. Absorption, pretty good, cuts us down to like 2 possible problems. Really in this class it's only 1 because we're not doing like particle absorption on surfaces, but that's the other place where absorption happens, where it's like, you know, you throw something at, you throw one thing at another and they stick together because there's like some absorption, and we don't do that so much. Molar absorptivity, Beer's law, right? Anytime we see the term molar absorptivity, it's Beer's law. And that's the only place where epsilon, this molar absorptivity, comes up. What is the other thing that's always implied with Beer's law unless it's explicitly stated?
Is it the 1 centimeter?
Yeah, path length. Again, you notice this problem didn't tell us that it was a path length of 1 centimeter, but unless it tells us it's not 1 centimeter, it's 1 centimeter, right? Standard spectrometers have a 1 centimeter path length. Unless something changes, and they explicitly tell us it's changed, 1 centimeter path length is implied. So that's the implied information. When I look at this, I've got some place where I'm going to use A. I've got some place where I'm going to use epsilon. I've got a concentration I can solve for. The thing that's weird, and I talked about this earlier in office hours, but I'm going to talk about it again real quick. We didn't use the lambda max. What's up with that? Did we forget something? Or is it conceptual?
Yeah, like, is it not needed for this?
It's not needed in the math, but it's needed in the concept of what's going on.
Okay.
So you notice it gave us the lambda max twice
The,
in the problem.
oh, yeah.
It said, for this absorption in this epsilon, lambda max is a connecting idea. If you remember in our spectroscopy lab, we had this situation where it was like, hey, which absorbance do you use with which peak? Which epsilon do you use with which absorbance? And it was like, well, we want to use the absorbance that corresponds to this epsilon. And so we used the wavelength, the lambda max, just made sure that we were using these two things with each other properly.
Okay.
So as long as the wavelength is the same, we don't need it because it's telling us these two things relate to each other.
Mhm.
If it gave us the absorbance at one wavelength and the epsilon at another wavelength, that's really weird. We can't actually do that problem.
Okay.
Because we don't get into the process of like, well, how can we calculate, like, can we make a relationship between those two? Right, so as long as the wavelength isn't changing, it's saying, hey, I'm using 516 as my reference for A, and 516 is my reference for epsilon, then my A and my epsilon relate to each other. I don't need the wavelength anymore. It's done its work. Now I can just plug my numbers in. So we plug our numbers in. I like to rearrange before I plug numbers in, so I'm going to take this and rearrange it. So I've got my concentration is equal to A over epsilon B. I don't know why. I seem to make less mistakes when I rearrange first. You don't have to. You can plug your numbers in first, but that's just me. So now I just plug in. My absorption is 0.442. My epsilon is 8982. My path length is 1. And we can put in the units here as well. This is going to be liters over moles, centimeters. This is going to be 1 centimeter. So notice my centimeters cancels out, and I've got a 1 over concentration. That's just going to give me moles per liter concentration. Now I plug in my numbers. Right? And it turns out that mathematically, this is really easy. It's just 0.442 divided by 8982.
Mm-hmm.
A lot of people get hung up on the math, but it turns out the math is actually really simple this quarter. It's like multiplication, division, addition, subtraction. It's figuring out how do these words tell me which math I'm doing is the part, which is why, again, I'd say focus on the vocabulary and how the vocabulary connects. Because once I say, oh, plug in your numbers and solve this, everyone's like, that's easy. It's figuring out that that's what you need to do. That's the difficult part. And we end up getting a 4.92 times 10 to the minus 5 molarity. Hey, someone can take this chair too if you want the nice chair. I'm not going to be sitting for a while.
The units.
Yeah, so that's the last thing we need to check on. Is
that just says in molarity.
In molarity, then it's going to be the 4.92 times 10 to the minus 5. It might have also asked for micromolarity, right? And then it would be 49.2 micromolarity. I can do those conversions. I've taken this class 12 times, so I'm pretty good at doing those conversions in my head. If you took this class 12 times, you'd be pretty good at doing those conversions in your head too.
Mm-hmm.
I think I've taken it more than 12 times, but let's not get into it. I mean, I'm taking it twice this quarter, for crying out loud. So, right, again, the process becomes really similar of like identify what's given, what's the implied information, rearrange. The wavelength, we had to do a little bit of conceptual work there to make sure we understood what was going on with wavelength. Mathematically, numerically, it didn't matter for our calculation, but it was conceptually important. Other questions? We've been mostly looking at dilution and Beer's law so far in office hours today. We've done a couple problems. I've been recording it so you can see the earlier problems as well. But I'm always fine doing problems again. You said you had a lot of questions. Do you have another question?
I had a question about like the notebook. In the previous lab, it asked to upload like a file, like an image of the
Like a
notebook.
picture of what you wrote down in your notebook.
I didn't write down. Am I supposed to be like writing down data
Always.
tables?
Yeah. I find it's always valuable because I don't trust computers. I don't trust computers. I mean, I do trust computers to some degree, but I always like to have a paper copy as well, someplace where I write down my notes, someplace where I do the calculation. It goes back to what I said with like why this simple calculator is my
I
favorite.
wrote it down, but I wrote it down like very messily, like
Yeah, that's
not,
fine. Put
like
a picture of
like
that.
over like 4 or 5 pages of stuff.
That's what I wanted to put in.
Oh, okay.
Yeah.
That was thinking. I have to go soon though.
Okay,
But
no worries.
do you have more office hours before class tomorrow?
No.
Okay.
No. My office hours yesterday were weird because it was Monday, so it didn't happen.
Okay.
I know yesterday was Tuesday, but we were pretending it was Monday. Still the only campus where I've ever had this happen. The whole Monday, Tuesday thing. It's strange. Also, a couple of you just came in. I don't know, those of you who have been here, have you gotten most of your questions answered?
Yeah, I have.
Yeah. People who, actually, was this your main question?
Yeah.
Okay. People who just showed up, what kind of questions do you have?
Others do, just, I'm not prepared to
Okay.
yeah. But
No worries. And then did you have a specific question, or are you just here for general stuff?
I'll pull up.
Great.
Okay, so it's number 9 on MQ number 1, so
Okay, so this is going to be something about unit conversions. I'm going to erase the stuff that we've got up so far. I add one more thing onto the board for my keeping stuff on the board. The other one that we want to have up is A equals epsilon BC. That's Beer's law. Okay, so let's go ahead and take a look. These are the main equations we've been working with today, but we're going to do some other things too. So we're looking, you said 1.1?
yeah.
So we're looking at 1.1, number 9.
Mhm.
What's the question?
Liquid helium is used for many low temperature applications. And it says liquid helium has a normal boiling point of 4 degrees Kelvin. What is its temperature in Celsius?
Oh, okay. Okay, so this question, how do we convert from Kelvin to Celsius? I need an equation sheet. Can you hand me one of the equation sheets that's back there? Oh, like really close to you. Okay. So, here's the equation. So I look at the equation sheet. If this one's kind of strange for doing the whole explicit implied result thing, because the explicit is 4 Kelvin. The result is Celsius. The implied is just the equation that relates Celsius to Kelvin, which is on the equation sheet. And so what I've got is my temperature in Kelvin equals my temperature in Celsius plus 273.15. So I can rearrange this. I've got my temperature in Kelvin already, so I just do a rearrange. Or I've got my temperature in Kelvin minus 273.15. Ooh, that was weird. 515 equals my temperature in Celsius. So then it's just doing that subtraction. 4 minus 273.15, 269.15. Sorry, negative 269.15. Now, 273.15 is negative 273 Celsius is what's referred to as absolute zero, or like it's the coldest possible temperature. So this is a weird conceptual idea that we didn't talk about too much, but temperature is essentially a measure of how much molecules are moving. And so theoretically, you can say, well, can we get to a spot where molecules aren't moving at all, where you've completely stopped molecular motion? And the answer is, yeah, theoretically, that would be absolute zero. That would be no motion happening, 0 Kelvin. And then the Kelvin scale is just a modification of the Celsius scale. So that way, if you're in Kelvin, you never cross 0. 0 is the theoretical lowest value. Now, scientists do all kinds of interesting things with laser cooling, where they can get down to millikelvin now. They can get down to like 0.001 Kelvin. I think they can even get lower than that now. But they can't actually ever get to exactly 0 Kelvin. It's theoretically impossible. Or maybe it's theoretically possible, practically impossible. But yeah, so that's it. It's just recognizing which equation to use. I think there's a more interesting question. So there's some other kind of funny questions we could ask about, like, okay, so that's the temperature in Celsius. What's the temperature in Fahrenheit? Those are the only 3 temperature scales that people use. I was feeling rushed on Thursday, so I didn't talk about why I think Fahrenheit is silly. Fahrenheit is silly. So Fahrenheit was supposed to be the perfect biological temperature scale. It was made by a biologist a long time ago who made some mistakes. So 0 Fahrenheit is the temperature at which saline solution freezes. And since humans are kind of just big bags of saline solution, that's the temperature at which your body would start to freeze, is 0 Fahrenheit. -32 Celsius. And what would that be? That would be 251 Kelvin, right? That would be the point at which the human body would freeze. Saline solution freezes. Human body's not exactly just a bag of saline solution, but it's kind of related. And then 100 degrees was supposed to be biological temperature, body temperature. The story I heard is the scientist who decided to put the scale together, Dr. Fahrenheit, let's say, I don't know his first name, he took the temperature, the body temperature measurements of everyone in his family, including himself, and a couple of his neighbors, and said, great, that's what I'm going to use for 100. Not realizing they all had mild fevers. And so body temperature ended up being 98.6 instead of 100. Interestingly, on top of that, is human body temperature has been shifting down over the last 200 years. Average body temperature is now 98.2 instead of 98.6. I don't know why, but average body temperature has actually shifted down over the last 300 years. Some people say it points to the fact that humans are still evolving and we're becoming more energetically efficient, but I don't know. I don't know if there's other evidence for that. So, but yeah, so we could look at how we convert from this Celsius answer to Fahrenheit, but we'll almost always use Celsius or Kelvin in this class. Other questions? Specific questions, general questions? Yeah.
I have more question about the workshop.
Yeah.
How do you sign up for that?
So did you see the announcement I put on Canvas?
Like today?
Yeah.
Yeah, I saw that, yeah.
So there's a person you need to email that's in charge of getting the permission numbers enrolled. And so you need to email that email address that's on the announcement with your EMPL ID number and which section you want to add.
Okay, thank you.
Cool, yeah. Other questions? So you haven't asked a question. Did you come up with a question or you just came to listen to us?
For 1.1, question 18.
Question 18.
Yes.
Okay, switching over to, is it okay if I erase this? We good? So, number 18. This is one of the graded questions. Yeah, but we can still do it together. What's this question say?
It's a 600 milliliter beaker, has an inner diameter of 89 millimeters. What is the vertical distance between 100 millimeter marks on the side of the beaker. Give your answer in
What
centimeters.
was that inside diameter?
Inner diameter was 89 millimeters. The vertical distance of 100 milliliters.
Okay. Question number 1. Did you do number 12?
Yeah, I had trouble.
So I did post office hours last week. I posted a video of answering that question, but let's look at it again. I think it's always worth doing questions again, right? This goes back to that repetition thing. We don't learn it the first time we see it. We usually don't learn it the second time. It's 3 to 5 times we need to do something for it to start to stick. So let's look at this. And for this one, do I have, okay. So I don't have a beaker in there. Do I have a beaker over there? I do.
Yeah,
Okay, let's grab one of those beakers. Carefully handle it over here.
Which one, the smaller one?
Yeah, the smaller one's the 100 milliliter beaker. And there's like a leaf in there, but okay. So here's a 100 milliliter beaker. It's got a certain opening to it. I'm showing the people on, like, you know, office hours later if you're watching. And we just want to figure out, oh, this was a 600 milliliter beaker, not the 100 milliliter beaker. So we just want to figure out the distance between marks here, right? And so there's kind of 2 different ideas we put together to figure this out, right? So we've got to figure out what's implied that we don't know. And we got to think about, well, what are we explicitly told? And we want to know what result do we want to get to. Okay, so the result we want to get to is the distance between these marks. What shape is this? So how do we talk about the volume of a cylinder? If we wanted to talk about going up this dimension, what dimension would we call that? Height. Yeah, we call that height. So the result we want to get is we want to get some height number associated with this. That's what we're trying to get. The thing we're told explicitly is we're told that the inner diameter is 89 millimeters. And we are told the volume between the marks that we want to consider is 100 milliliters.
I think it's 81. Oh no.
It's different for different people.
Oh. Okay.
Yeah. So if you tried to copy somebody, it'd be wrong.
Okay.
But depending on
I was looking at mine. I was like,
Yeah,
mine
yours-
says 81.
yours is 81 for the inner diameter. It might be a different size beaker too.
Yeah, it's 600.
So this one is 600 milliliters, but we're looking for the 100 marks. There's some people who got 100 milliliter beakers. There's some people who got, I think, 50 milliliter beakers. Randomized problems. So, but it's all the same concept behind the problem of how do I figure out the distance between the marks of a cylinder. So we look at this and we say, okay, what's the implied information? What's the volume for a cylinder?
Pi r squared h.
Great. Now let's see. One of the things that is also implied is radius equals diameter over 2, right? It just assumes we know. I just assumed you knew that already, right? Now when I look at this, I've got a volume, I've got a radius, I need to solve for height. So when I start thinking about this, I'm like, okay, I've got my volume, I've got my radius, height's what I'm solving for. I actually know everything. So I can just rearrange this equation. Now this one I don't rearrange. Oh no, I can just rearrange this equation and solve. So I can do volume divided by pi r squared equals height. Now the thing we have to be careful about in this problem, once we have this, is pretty straightforward. I plug in my volume, 100 milliliters. I plug in my radius, 89 divided by 2. And the thing I have to be careful about, the square and pi, and those things we're pretty good at. There's something we have to be really careful about though, which is the real trick of this problem.
The units?
The units, right? This is in millimeters. Milliliters here, I can write 1 milliliter equals 1 centimeter cubed. Centimeters and millimeters isn't matching up. So that's the real thing we have to be careful about here, is the fact that the units don't match if we're not careful. So let's go ahead and make our units match. For me, Actually, I'm going to ask something. Does it want the final answer in millimeters or centimeters?
Centimeters.
Oh, okay, great. So it wants the height in centimeters. So it's going to be easier for me to switch this 89 into centimeters, and then everything will be in centimeters. So that's going to be 8.9. Again, I can just do that one in my head. I'll do it over here. 89 millimeters times 1 centimeter has 10 millimeters in it. I just know that one. If you need to go from millimeters up to meters, then meters back to centimeters, that's totally fine as well. You end up with a factor of 1/10, and you get 8.9 centimeters. Now, my centimeters matches my centimeters, and my centimeters matches my centimeters. Everything's in centimeters. I avoided that problem. So we can go ahead and do 100 centimeters cubed divided by pi times 8.9 centimeters squared. Notice 2 centimeters cancels out. We're going to be left with an answer just in centimeters. I messed up. What'd I mess up?
Is that milliliters at the top?
1 milliliter is 1 centimeter
Oh.
cubed.
The exponent?
What's that?
The exponents? No.
No. It's a really silly mistake that a lot of students make, and I made it. I didn't do it on purpose, but I'm going to use it as a teaching unit, teaching moment.
Did you divide by 2 for the diameter?
I forgot to divide by 2 for the diameter. I left it in diameter instead of radius. So let's go ahead and plug in that divide by 2. I'm going to have to erase this and rewrite it so I can fit it in. I'm going to erase that too. So I'm going to have 100 centimeters cubed divided by pi times 8.9 divided by 2 centimeters squared equals answer in centimeters. Now I should be okay. Let's go ahead and plug some things in. 8.9 divided by 2 times pi inverse times 100 Did I do that right? 8.9 divided by 2. I think I forgot to square that. Squared times pi inverse times 100. Yeah, that's better. I got an answer that was like 7 centimeters, which would be like 3 inches. And I was like, that's how far apart the marks are? And it's like, not really. Like a 600 ml beaker is like, that big. So I got like the entire height of the beaker. It was because I forgot to square the first time I did it. 1.60. Right? This centimeter squared is going to cancel out 2 of the centimeters on top, so I left with 1 centimeter for my height. Does that make sense?
Yes. It helps when you know the implied part.
Yeah. So the funny part is, and this is kind of one of the awkward things with this problem, is for me, I meant the difficult, like tricky part of the problem to be the unit analysis, but it seems that most students get caught on the shape of the volume of a cylinder. And I'm like, wow, that's not what I meant for the hard part to be. But that ends up being the hard part for a lot of the students. Whereas like for me, the part that I meant for to be tricky was centimeters versus millimeters. Okay. Other questions? What time is it? 3:30. Okay. Other questions? We still have some time. If you don't have questions and you just want to work on a couple things until you have questions, that's a totally fine thing to do during office hours. I'll pause the video until you come up with specific questions, but you can just work through homework problems and lab problems. Okay, so a quick checking on 2 problems. I'll take that. You can grab your bag. So just doing a quick check on 2 problems. Were those from MQ?
One was from the 1.1 and then the other one was 1.2.
Okay, So and they were both number 8s. That confused me for a second. Okay, so we're looking at number 1.1, number 8. This one confuses a lot of people, again, because the implied information is stuff I thought you knew from physics classes in high school. But if we didn't know that implied information, we can kind of figure it out from the explicit information, because we're told the speed of light is 3.0 times 10 to the 8 meters per second. That's the speed of light. We are told that the distance it travels is 1 centimeter, right, because it's a standard cuvette. And then the result it's asking us to get is some amount of time. So the thing that's implied here is velocity times time equals distance. That was the thing that was needed. And then we just do a rearrangement of my time is equal to distance over velocity. And we have to be careful because this is v for velocity, not v for volume. Right? So then I can just go ahead and plug in my things again. I got to be careful about units. I've got meters, I've got centimeters, and I want the time in nanoseconds. So first I'm just going to solve this in terms of seconds, and then we'll convert to nanoseconds. That's always safer for me. So I'm going to go ahead and do time is equal to 0.01 meters divided by 3 times 10 to the 8th meters per second. Meters is going to cancel out. 1 over seconds becomes 1 over 1 over seconds becomes seconds. And I get some answer for that. 0.01 divided by 3 times 10 to the 8th. Ooh, was that right? Yeah, that's right. Okay. So we end up getting 3.33 times 10 to the minus 11 seconds. Did I do this right? Velocity times time gets us distance. We are given a distance of 1 centimeter. Why do I feel like I messed something up? Whatever, let's just keep going. I feel like I messed something up, but everything is working out fine. I just thought it was going to be a bigger number than that. Now it wants an answer in nanoseconds.
It's how long does it take in nanoseconds for light to travel 1 centimeter?
Okay.
Do you have to convert 3.0 times 10 to the 8th meters over seconds to centimeters?
No, I converted my centimeters, right?
Okay.
So what I did was I took 1 centimeter, and I said 1 centimeter is 1 meter is 100 centimeters. So I converted so that way it's meters and meters cancels out. Now I'm going to take this 3.33 times 10 to the negative 11 seconds, and I'm going to say 1 nanosecond is 1 times 10 to the minus 9 seconds. Divided by 1 times 10 to the minus 9. And I'm going to get 0.0333 nanoseconds. Hopefully I did that right. I thought it was longer than that, but I might just be remembering it wrong. Now, when I glanced at your work, I said, oh, it looks mostly right, but I wanted to be careful. Does this kind of track with your work?
Yeah.
Because I saw you had you kind of built the nanoseconds conversion. I saw you had like I saw you had everything correct, but I wanted to do it on the board to double check. Did it track with what you got?
Yeah.
Did we get the same number?
I got, from like previous attempts, I got 0.0333. But when I would enter that into LabPal, it would just mark me wrong.
Huh.
So
I'll double check that. I think we did everything right. Unless we're missing some detail in the problem. I know there's a second problem that uses a different speed for light. That's like number 11 or number 13, something like that. Because it's doing it not in a vacuum. So that's that one. I also wanted to look at number 8 from 1.2 real quick. just for the unit analysis to show where things went wrong. Is it okay if I move on? Okay. So then we'll go ahead and look at (1.2), number 8. And then this one was a Beer's law rearrangement. So we had Beer's law, we rearranged. So we had, were we solving for?
Concentration.
So we got concentration is equal to A over epsilon B. If I'm remembering my units correctly, this is 0.442 divided by 8,982 times 1. I got a little bit lazy with my units, but forgive me for a moment. And we end up getting an answer of 0.004921. That should be units of molarity. And so the point where confusion came was, what, Abby?
Yeah.
What Abby had written down was just 4.92. And you plugged in the units for molarity as moles per liter, which is totally fine. You just forgot your times 10 to the minus 5 because of the 1, 2, 3, 4. Oh, did I forget a 0? Let me plug it into the calculator real quick. I think I forgot a 0. Or maybe it's only minus 4. 0.442 divided by 8982. I did forget. There's supposed to be a 4 0. And that gets us to minus 5. Yeah. So yeah, I forgot a 0. Trying to trust my memory, always dangerous.
Thank you so much.
Hey, you bet. See ya. So, just being careful. This is a really common mistake where people, I don't know if we do it in our heads or if your calculator is already put into scientific notation, sometimes you miss the little bit that's off to the side. So make sure you're keeping your times 10 to the minuses on there.
For the quizzes, we're only allowed to have calculators like that.
For the quizzes?
Or, I mean, yeah, for like the...
For the quizzes, you're allowed to use any calculator you want. It's open note, open book, but not open internet search, not open collaboration.
Mm-hmm.
So you're not supposed to be asking help from other people or help forums or the internet or ChatGPT, anything like that.
Mm-hmm.
For the exams, I recommend these calculators. You can use programmable calculators as long as the memory is cleared and they can't connect to Wi-Fi.
Okay.
Because there are some fancy calculators that are pretty much little computers that can connect to Wi-Fi. Those are not allowed. Okay. Ooh, we've got a little bit. I can see the sun is getting on the board. So I think that means time is pretty much up. Are there other last minute questions?
Yeah, actually,
Yeah.
Well, one, so what's the difference between molarity and molar absorptivity?
Okay, so molarity is a unit of concentration, right? So that's moles per liter, right? This part in blue is concentration, molarity. Molar absorptivity, which is often just called absorptivity, is this constant of the material. The reason, and I know I should change, but I like calling it molar absorptivity because I feel like it describes what's going on really well. So molar absorptivity, if I rearrange this equation to isolate epsilon, that absorptivity, it's epsilon equals A over CB, right? And I'm writing the B a little bit off to the side and small to kind of give us this idea. Molar absorptivity is this relationship between the molarity and the absorption. So the word molar absorptivity really describes what it is, right? It's a relationship between molarity and absorption. We call it the molar absorptivity, or the absorptivity. And so it's a physical property of the material that changes when you change the material. So we could have red dye and blue dye, and we could set them up so they have the same concentration, but they're going to absorb light in different ways because they're different materials. So they might have the same molarity, they're going to have different molar absorptivities because that's a property of the material.
How did you get cubic millimeters to 100 cubic centimeters?
Oh, so that was, okay, that was a previous question. So that is using the definition. So when we have 100 milliliters, we can use the definition. There's this definition that's kind of simple. So I do this conversion in my head and I just put it on the board real quick, where it's 1 centimeter cubed is 1 milliliter. So whenever you see ml or cm cubed, you can just kind of change them back and forth because it's a 1-to-1 ratio. So that's just 100 centimeters cubed, right? My milliliters cancels out. And then I can convert it back just as easily where I've got 1 milliliter for 1 centimeter cubed. And that equals 100 milliliters. Right? And that's because a milliliter, this volume is defined as a cube that is 1 centimeter by 1 centimeter by 1 centimeter. That is the definition of 1 milliliter. By definition, so like even though I've only got one digit here, it's technically infinitely precise because it's a definition. So I could add like a billion zeros, 1.000000000, because that's a definition. And that's how we define what a milliliter is by saying it's a cube that's 1 centimeter by 1 centimeter by 1 centimeter. Now the place where people get confused with this is they bring in the density of water. And the density of water, the density of H2O, is approximately 1 gram per 1 milliliter. But that's only true for pure water. You put some blue dye in there, it's no longer 1 gram per milliliter. You put some salt in there, like the ocean, it's no longer 1 gram per milliliter. You increase the temperature too much, it's no longer 1 gram per milliliter. This, always true. Other questions?
Yeah, I had a question.
Yeah, go for it.
So number 7 on 1.1
Mm-hmm.
says 1 atom of gold weighs 3.27.
Yeah, let's do that one real quick. I'm going to erase all of this. We're going to do back to 1.1. Number 7, 1 atom of gold.
Yeah, weighs 3.27 times 10 to the negative 13 nanograms.
You said 3.27 times 10 to the minus 13 nanograms.
Yeah. How many gold atoms are in 1 gram gold?
Is it in 1 gram? How many?
Yeah, 1 gram of gold, yeah.
AU is the symbol for gold. I just got tired of writing it out. So here's what we do. How do we solve this? So I'm going to rewrite things a little bit, and that is I'm going to rewrite this sentence as 3.27 times 10 to the minus 13 nanograms per 1 atom. And I want to get eventually to a number of atoms. So this is going to be a complete unit analysis problem, where I just need to get my units to cancel. Now, I know I have 1 gram of gold. Can I get, if I want atoms on top and I want to cancel out grams, is this the right way to write this down?
What did you need to convert it into grams?
I need to convert it to grams and flip it over, right? Because I'm gonna want grams to cancel out, and I'm gonna want atoms left over on top. So we need to do 2 different things. First, let's go ahead and convert the. Well, let me flip it first. So I would want 1 atom per 3.27 times 10 to the minus 13 nanograms times 1 gram equals the number of atoms. And I've got two options for what I convert. I can convert nanograms to grams, or I can convert grams to nanograms. As long as my units match up, they'll cancel out. And I'll be honest, converting things in fractions always mess me up. So I'm going to convert this one to nanograms. And that's easier for me, and my units will still cancel out. So I'll just pop over here real quick, and I'll do 1 gram is equal to, let's see here, times 1 times 10 to the 9 nanograms per 1 gram. Since everything's is ones, I can just go ahead and plug that in. This is going to be 1 times 10 to the 9 nanograms. Now I just do 1 times 10 to the minus 9 divided by 3.27 times 10 to the minus 13. Before we do this, are you expecting a gram of gold to have a lot of atoms or only a few atoms?
A lot.
A lot, like billions and billions and billions. So I'm going to do 1 times 10 to the 9 divided by 3.27 times 10 to the minus 13. And I'm going to get 3.05, 3.0, we'll call that 0.6 after we do the rounding, times 10 to the 21 atoms. Right? That's a lot of atoms, which makes sense because atoms are really small and a gram is relatively big. So this one was mostly unit analysis with this trick of being able to translate that sentence, 1 atom of gold has that number of grams, into a fraction. Cool, okay. Well, that's all we got time for. I'll go ahead and upload this video pretty much right now, so if there's anything you need to review,